I'm Sophie Thomas. I am Director of Circular Design at the Useful Simple Trust, so Useful Projects. We're a consultancy. I've spent the last 25 years working in sustainability, resource efficiency and circular economy. I established about 10 years ago, I ran a program with Innovate UK, which is now UKRI, and the RSA, which is just over there on the other side, the Royal Society for I can never remember the name of Arts, Commerce and Manufacturing, and we ran a program where we investigated the role of circular economy for designers, like what impact does it have? What's the point of bringing designers into a process of like redesigning things? And I'm still not getting this thing. This is good, isn't it? So I'm going to ad-lib the whole thing. Brilliant. And actually, the reason why I said to Alfredo that I would come and talk to you about this is that one of the areas that we're working in the trust, so I work with lots of different people. I work with brick manufacturers, I work with plastic supply chains, I work with textile designers, leather, all these different people. And the very particular reason that I work with them is because I start looking at the end of life, so I start at the end, at waste, effectively. And because of the work I've done, I'm now chartered waste manager. So I've moved on from being a graphic designer. And this is me in my local habitat. This is actually in a material recycling recovery facility in Athens. So we're here, we were looking at the plastic problem in oceans, particularly. This is pretty obvious. It's a climate emergency. The interesting thing is that we will say tech will save us from all of this. But what are the implications of that? 20 years ago, actually, I was working with a chemist, Mike Pitts, who now still works at UKRI, and he showed me these slides, and I think this is really interesting. So this is the kind of, I would say, the building blocks for designers. This is our periodic table, and actually, just to remember, I actually bought my fan, which has got the periodic table on it, which is super useful. And he said, this is what our periodic table could look like in 80 years. Because of the way we're using our elements and because of the way we're not thinking about it in a closed loop. So this is about the take, make, waste, linear economy. And now, that was 20 years ago. We knew that there was tech issues coming up. We knew we were going to have to rely on electric vehicles, wind turbines, all of these things put great pressure on all our elements, and you can see this. And I'm going to talk a couple that are really important: nickel, indium, gold, platinum, neodymium. These are all the rare earths down here. Really, really quite worrying as a graphic designer. I'm not going to have, as a designer, so I'm not going to have much to work with. As industries, we're going to be struggling for this. We know the prices are very volatile as well. And now we have what's the critical elements list. So every 3 years, Europe brings out the whole list of what are the sort of real pressures on a lot of the elements that we have on our periodic table. Currently it's 30. When I started working on this, it was about 21, so it's really sort of ramping up. The interesting thing about the critical elements list, which you can look up, it's online, is that it only looks at today. So it's not looking at future pressures, it's just looking on what the issues are right this minute. So if we look at things like the World Bank Group have been doing some stats on mining, particularly in rare earths, particularly in lithium, we were looking at that. We've gone from the current production of 43 kilotons. By 2050, we're going to have to up that by 965% because of the demands that we're going to put on it in terms of new tech. Also, cobalt's a big one, 585%. Neodymium, 37%. Indium, 241%. How much do you think indium is recycled currently in the United Nations? Does anyone know? Less than 1% is recycled. It's a very, very difficult material. These are scarce materials in the sense that they're abundant in the earth, but they're very hard to extract. And they're used in very small amounts across all of our high tech, so they are quite hard to get out. The environmental impact of this stuff, I've just been reading some pieces around rare earth mining. We know that China, for instance, holds about 95% of the rare earth mining currently. Now, rare earth mining is particularly bad. We either scrape off the topsoil, pump in loads of chemicals, and they help leach. So you get these kind of leach ponds, and the leach ponds and the extraction, so they kind of bind together the chemicals, and they pull out all of those, and then they process them, and you get your rare earths come out of it. Or you drill a hole with loads of PVC pipes and you pump those chemicals into the air. That's like your ammonia, your sulfates, your hydrochloric acid. For every 1 ton of rare earth that we create like that, we have 2,000 tons of toxic waste produced. That's in the air, that's in the water, the earth, etc. So it's pretty horrible. And we're not very good at cleaning them up yet. We don't really know. There are a huge amount of leach ponds just hanging, like full of all this stuff. Old ones as well, which haven't been lined properly. So it's not a great story, is it? I mean, that's the thing. We have this great problem at the moment that we are really, really hoping that this climate emergency has to be solved. It has to be solved with renewable energy. It has to be solved with electric vehicles. We have to go clean, but we're not really considering the other side of it. Even the social aspect, extraction mining is not a very clean industry at all. And it's not just that, everything we have around us, we've heard a bit about that from this great speech earlier, it was about the amount of stuff that's behind our stuff. So for instance, I do a lot of work around toothbrushes. Don't ask me why. I think because they're very ubiquitous. Everybody has one. Everybody changes theirs, hopefully, every 3 months. Kind of hoping you do. But they're very hard. They're one of those products that has 4 different types of plastic in it, often has metal pins in it or glue, can't go into any particular bin, ends up in the landfill, often ends up floating. I've picked out about 18 from a walk down a beach, Camillo Beach, which is the closest beach to the Pacific garbage patch, in half an hour. So that's kind of why they're quite an interesting object. But there you go, there's 1.5 kilos of raw materials in one toothbrush, and yet we all use them we have this kind of constant flow of these products. We don't really understand the footprint behind all of our stuff. So that's what I've been doing for the last 10 years. I've been taking things apart, looking at what's in them, working with designers, working with industry, working with chemists, technologists, businesses, anthropologists, policymakers to see actually how we can design things. And often I work backwards. So I start on the waste tip, as you saw. I grab something, get a screwdriver, take it apart, see how easy it is to get all those elements. And then we have all these element cards to work out what the scarcity issues are, what are the pressures on those materials. With something like this is quite easy to do. This is a toaster, right? £15 in Argos, super cheap. The most valuable thing in that toaster was probably the breadcrumbs at the bottom. There was nothing that we could salvage, really. It was really quite astonishing how cheaply made it was and how hard it was to take apart and how impossible it was to extract any value out of it whatsoever. And that is part of the problem, that a lot of our stuff is either hidden away and we're told not to reuse this with no explanation whatsoever, or it's so tiny. This is a motor that contains neodymium and copper. Look, it's about that big, and it came from a disposable toothbrush that we had, the ones that kind of vibrate and you kind of put a battery in them and they're complete. Never ever buy those. Disposable electric toothbrushes, don't want to see anyone in this room ever use one because A, they just make your hand vibrate, so they don't even work. They have a battery in them. You can't change the battery because when you take it off, you break all the seals on it, and it's got this stuff in, so not a great idea. As I said, that's the same materials that have to go into these things. This is the future. This is what we want. But currently sits in all this stuff. Broken hoovers, candy floss makers, all this kind of stuff. And these guys are trying to save it all. These are the guys at the end of line guys. These are the guys who I go and see regularly who are, trying to build a battery recycling facility up in Minworth in the West Midlands. Or this guy is in Kent, who's an e-waste recycler, and he's actually storing loads and loads of indium screens because he knows that although at the moment we can't get it away, it's very uneconomically viable to get that stuff out because we haven't got the scales working yet, and it's too expensive, but he's holding on to it because he knows we're going to need it. Why is that important for design? Because 80% of the environmental impact of all the products, of everything that we do, is predetermined when people like me start to think about how I'm going to design something, start to think about how that electric vehicle is created, start to think about that particular piece of clothing, how it's sewn together, etc. And so I just want to end on one thing, like lessons to learn. This is quite, we're going to be looking at particularly about the electric vehicle battery. And we're going to sort of have a look at, there are some really good examples. One of the examples, for instance, iPhones, like 50 elements in an iPhone, some stuff that was in there now that, when the iPhones first started, they were like, we don't know what this element could do. I've got this 1960s periodic table that has yttrium on it, and they go, we don't know what we'll be using it for in the future, and now you'll find it in your iPhone in your pocket. But this kind of obsolescence cycle is one of the things we're going to have to break. And actually, Apple are looking at that. They've started to build the robots that can start to disassemble their pieces, and they now put in about 90+% of recycled rare earths in their phones. So they've worked out a way from a reverse design process to actually understand how we can recover that material, and that's really important. So here we are, a nice lead acid battery from a car, really old technology. Actually, very, very small amount of ingredients in this. Not great. Acid, lead, really bad. Honestly, the kind of informal recycling of lead acid batteries is absolutely terrible in a lot of developing countries and really needs to be sorted out properly. But what's interesting about this product is you can go online and find out how to fit it again. So basically fix it and make it usable as your household battery for storage. And this is another thing that we're going to be thinking about. How do we store that energy that we're going to need? So you drain out the acid, you can melt down the lead, you can you can buy the new kind of molds for it. I really don't try this at home, honestly, it's really bad to do. But you can get it back to a battery. And here we have an electric vehicle battery currently. Now they are massive. I don't know if anyone's ever seen one. They are literally the whole bottom plate of the car currently. Very, very big, very complex, very difficult to recover. So these guys, there are about a couple of plants in Europe where they can take them. They very carefully depower them, unscrew them, lift them out with cranes, then bung them in the crusher. All these beautiful materials, all these things that they've very carefully put together, they bung in the crusher. This is how we deal with electric e-waste currently across the board. We just crush it and try and separate out what we can. So all of those wonderful materials end up in these kind of elements. So they don't just crush it, they put it through a multi-million-pound facility, which actually helps to pull out all the metals, take all this stuff out. Very expensive if you think about the lead acid battery, where actually it's a very simple product. We just need to formalize the process of remaking it, of making it work again. Whereas here, we haven't got that. We've just taken it back to some materials that we've just about managed to scrap together, including what's called the black mass at the front. And these are the rare earths. So even when we've done all that multi-million-pound of processing, we still end up with 4 materials stuck together. So this is the issue, and this is the challenge that I'm throwing all to you.
Before you go, can you give us a more hopeful ending?
Oh, yeah, sorry, yes. I can actually, because I was just reading about the alternatives for rare earth, which is really interesting. So there's a Harvard team that are working on extracting rare earths with using bacteria instead of chemicals, which is really interesting because that's such a big problem.
I was going to ask, that's a sort of synthetic alternative. Let's make those materials another way.
Yeah, that's another way. And then there's another team which are looking at, in Purdue University, that are extracting rare earths from coal ash, so not even have to mining this material in the first place. And also there are some other stuff. So the iPhone is a very good story because they've actually, because of the way they've looked at the design, they can actually now extract and recycle the rare earths in their products.
It's not good for their brand or their future to just keep pumping them out anymore, isn't it? They need a new story, a new fresh angle.
Do. They need to have a proper closed-loop circularity for phones, for everything, I think. And, I mean, the BMW 5th generation electric vehicle actually has eliminated rare earths altogether.
Yeah.
So that's very interesting, to see where that goes. But I think in the end, it's about actually, what I was trying to show there is like we don't learn lessons from things that actually do work but need to be upgraded. Yeah. And actually we should take stock of that and see, what works, what doesn't. Yeah. Complexity and circularity are always very difficult. They're just, you have to embrace it, yeah. But you also have to really, try and simplify. It's about monomaterial, it's about the way things connect. Yeah. So, it may sound very depressing, but it's a really interesting challenge for designers and for technologists.
Yes. Sophie, everyone, thank you very much. That was brilliant.